Hello, my name is Behnaz, and I'm a PhD candidate in computer science at Loyola University, Chicago. Today, I'm excited to share our work titled Enhancing Clinical Concept Extraction with Spark NLP and LLMs. This research presents a hybrid NLP LLM framework designed to bridge the gap between unstructured clinical narratives and structured biomedical knowledge bases like UMLS and SNOMED CT. We somehow combine Spark NLP's precision named entity recognition with the contextual reasoning of LLMs, in particular, LLaMA and Mistral models. So, before we get technical, let me give a brief introduction. In general, I work at the intersection of AI and biomedical informatics, building intelligent systems that transform free text medical notes into a structured, machine readable representations. So it means that ultimately we try to support clinical decision making and interoperability. In doing so, with that background, let's explore why clinical concept extraction matters so much today. And of course, in this presentation, I'll talk about it. Maybe you ask yourself why clinical concept extraction, and I'm wondering whether you are familiar with clinical notes or not. What you see, nearly 80% of all electronic health record, that we call it EHR data, is unstructured text, including physician's notes, progress reports, and discharge summaries. These notes are rich in insights, but because they are free text, they are often underutilized. And then we can automatically extract medical concepts such as diagnosis, symptoms, and medications. From those narratives, we somehow enable downstream applications such as clinical decision support, patient phenotyping, and population level analytics. But right now, much of that potential remains locked inside unstructured text, and our main goal is to unlock it as efficiently as possible. But we talked about the clinical notes, and of course, like many other kind of data, we have some sort of challenges in clinical notes. To be more specific, they are linguistically complex and full of inconsistencies. But what kind of inconsistencies? For example, we have abbreviations like NVD, meaning nausea, vomiting, and diarrhea, and multi-word expressions like chronic congestive heart failure, and modifiers such as severe or mild that you see, change clinical meaning. And the most important issue that currently we have is negation. For example, no cough denies pain. And to this, the fact that each clinician writes in a personal style, and I can say that clinicians have their own signature. And because of that, we get highly diverse, context dependent language that challenges even the best NLP models, and somehow it's inevitable, to my mind. But now, uh, we talked about the challenges, and before talking about the new tools that somehow help us to solve dimension issues. Previously, there were several rule-based tools, and of course, they had their own limitations, like CTEX, MetaMath, and SciSpace. Of course, there are some other tools, but now I just talk about these tools. You see, these tools work well on standardized or formalized tapes and offer high precision, but their recall is low They often miss valid concepts and they produce false positives, sometimes nearly 30%. For example, C-tapes may recognize nosebleed correctly as epistaxis, yet it tends to split severe chest pain into separate entities or misinterpret abbreviations. So they're accurate on the surface, but somehow brittle when language gets messy. And to move beyond those limitations, we built a hybrid framework. And our hybrid framework, if I want to talk about the objective and approach behind it, I can say that we focus to improve concept extraction by combining Spark NLP's biomedical NER models with LLM-based semantic reasoning. After detecting candidate concepts, we map them into UMLS and SNOMED CT ontologies for standardization and mapping. This hybrid design merges the rule-based variability of Spark NLP with a contextual understanding of large models, and somehow it's a best of both worlds approach. Furthermore, what makes our framework distinctive is its zero-shot design. What does it mean? Actually, it doesn't require retaining, and we rely on prompt engineering. And I think that today you heard about the LLM and prompt engineering. Moreover, we rely on clinician validations to ensure the quality. That makes the method scalable and domain adaptable, and we can reuse it across institutions or data sets without costly fine tuning. Okay, before diving into our hybrid framework, first of all, I just want to answer this question: why LLM? Here you can see some of the advantages of the large language models. Actually, they are context aware, so they can understand abbreviations, somehow negation, and complex phrasing. They are generalizable, adapting to different node sections or specialties. Furthermore, they perform zero-shot reasoning, making them efficient for new tasks, and they are semantic, meaning they understand meaning beyond the exact word matches. And something a rule-based system that couldn't do it as efficiently as possible. By the way, all of these properties make LLMs perfect candidate for concept extraction at a scale in our hybrid framework. But we talked about some of the explanation, definitions, and the approach beyond our hybrid framework. But on what kind of data we worked on? To evaluate our system, we focus on using the mimicry dataset. It's a kind of benchmark dataset, and actually, it's an open, de-identified ICU dataset containing a wide range of clinical notes. It contains discharge summaries, progress notes, nursing notes, radiology records, and etc. And among all these kind of note types, discharge summaries are the richest. They are comprehensive. Physicians authored records summarizing diagnosis, treatments, and outcomes. That's why our study focused specifically on discharge summaries, and they because they capture the entire patient journey and they are so rich. We talked about the hybrid framework, the objective, and the approach about it. But on what kind of data we worked on? To evaluate our system, we use the mimicry dataset, an open de-identified ICU dataset containing a wide range of clinical notes. including discharge summaries, progress notes, nursing notes, radiology reports, and etc. But you see, among all these kind of note types, discharge summaries are the richest. They are comprehensive, and the physician authored records summarizing diagnosis, treatments, and outcomes. That's why our study focused specifically on discharge summaries because they capture the entire patient journey. It's good to know that discharge summaries have several sections, and here we just focus on three sections, including chief complaint, that we call it CC, brief hospital course, DHC, and history of present illness, HPI. Together, these sections span different lengths and complexities, allowing us to test model performance across both concise and richly detailed clinical narratives. So, Figure 1 somehow shows you the pre-processing pipeline of our work. And as you can see here, we started from raw notes and changed those kind of notes to a structured concepts. But how? We start with raw text, break it into sentences, tokenize and generalize contextual embeddings. Then we apply Spark NLP's NER model to identify entities such as diseases, procedures, and anatomical terms. These identified entities are organized into chunks, essentially the text segments that form the foundation for further concept mapping. So, we move from messy narrative text to a structured concept candidates and ready for LLM reasoning. And here, this is the complete hybrid framework. Uh, In our framework, Spark NLP extracts the named entity chunks. Each chunk is transformed into embeddings using sentence word. After that, those embeddings are matched to candidate terms in SNOMED CT using Spark NLP's resolvers. Next, we feed the chunk and candidate list to an LLM, either Mistral or LLaMA, guided by a custom prompt. Finally, we verify the chosen concept using the UMLS REST API, retrieving the preferred term and concept identifier. This integration ensures somehow each extracted term is contextually accurate and semantically standardized, and critical for interoperability in EHR system. Just one more thing about our hybrid framework is that in our framework, uh, we just use the Llama and Mistral models in our LLM section in order to generate the response. And in the next slide, we can see some of the results of these models. But we created a hybrid framework, and actually, the most important part of each system and each tool is validation method. In order to do the validation, we had three physicians from different specialties who labeled every chunk concept pair. They used five categories, including correct, partial, incorrect, missing, and spurious. And of course, we had some sort of rules. And if clinicians didn't fully agree, we applied a silver standard rule. And somehow, if at least one labeled it correct or partial, the system received partial credit. This way, Evaluation better reflect clinical judgment rather than binary correctness in our system. And regarding the evaluation metrics, we had three metrics: precision, recall, and false positive rates. As you know, these equations have their own equations and formula, but in our framework, we try to use have some other kind of equation for precision, recall, and false positive rate based on the categories that physicians assign to the concepts. And as you can see here, we have all five different categories: correct, incorrect, partial, missing, and spurious, but in different format. And we try to calculate these metrics based on these categories that we had in our framework. So, and after calculating the metrics for LLaMA, Mistral, and CTEX, as compared to Mistral and CTEX, LLaMA had better results. Actually, it had best F1 score and with lowest false positive rate. It's good to know that CTEX had a similar F1 score like LLaMA 3.18 billion in strike version, but with the highest false positive rate, around 30%. And because of that, among all these models, LLaMA had better results and it was the best candidate in our framework. So, uh, to make the previous slides more tangible, let's look at a few examples. For instance, CHF. Uh, Both Misron and LLaMA mapped it correctly to chronic congestive heart failure. And for COPD, again, they correctly mapped uh, this abbreviation to chronic obstructive pulmonary disease. But for CXR, everything was a little bit different. And Mistral produced brain radiography, whereas LLaMA identified it as a chest X-ray and the clinically precise term. This, differentiate shows how subtle contextual reasoning helps disambiguate concepts within a medical language of something. And I just wanted to show you, some of the results that we had in our framework. And to wrap up the presentation, it's good to know that from this study, three lessons stand out. First of all, LLMs outperform rule-based systems in handling abbreviations and modifiers. The second one was that prompt engineering is critical. Iteratively refined prompts substantially improve accuracy, and clinician validation is indispensable. However, it doesn't mean that we didn't have any other challenges, and actually we faced some sort of difficulties and issues in our work. And negation remains difficult. For example, in a note saying no cough, some outputs still predicted cough present. And still, it is a big issue that currently we have even with LLMs. And as for limitation, our dataset was restricted to three sections of mimic-tree discharge summaries, which may not capture all clinical styles or domains. So, future work will extend evaluation across broader datasets and integrate assertion detection enabling the model to distinguish present versus absent findings. In summary, our hybrid LLM framework tried to improve clinical concept extraction by merging Spark NLP's NER experience with LLaMA's contextual understanding. It somehow achieved higher F1 scores and lower false positive rates and demonstrated adaptability across very clinical texts. And at the end, I just wanted to thank my advisors, Dr. Tichimi and Dr. Diga, for their mentorship, support, and guidance in this research project and journey.